Hi there, and welcome to Chapter 8.1 from Stevens' Introduction to Statistics, the Think and Do book. In this chapter, we're going to build up the foundations of hypothesis testing, and it has a lot of terms and a lot of players, a lot of parts and pieces, and so this is sort of building a car one little piece at a time, where we describe all the little parts that go into it. If that's not your style of learning, if you just want to see some hypothesis testing being done, and then maybe piece together what's going on later, you could probably jump to 8.2. You'd be missing, you'd probably be missing some foundational stuff, but all of this build-up can be a tad bit overwhelming. So you might want to just see. There's also a good complete example at the end of this section that you might want to start with that, but we're going to start from the bottom and work our way up. Okay, so I'm going to go into full screen mode here. And we'll get the whole thing going. Lots of room. Okay. Foundations of hypothesis testing. In statistics, a hypothesis is a claim about a property of a population. And a hypothesis test is a standard procedure for testing that claim. They're also called tests of significance. And here's some examples. Let's go right to the examples. Number 1, a survey showed that of 150 randomly selected commuters, 55% use cell phones while they drive. The claim we want to make from that, we see the 55%. The claim we want to try to support is we want to claim that most commuters use cell phones when they drive. Maybe we want to put a headline, most commuters use cell phones when they drive. And so we're asking ourselves, is the 55% from our sample significantly greater than, is it far enough above 50% that we can use the word most with confidence? In mathematical terms, we're claiming that P is greater than 0.5, where P is the population proportion of all commuters who use cell phones when they drive. So this claim that most of all commuters use cell phones when they drive, is simply stated with this mathematical inequality. Okay, for number 2, we have a sample of 100 healthy adults. The mean body temperature from that sample is 98.3 degrees. The standard deviation of 0.9, and we want to claim, by the way, if you look at this, 98.6 is the conventional healthy body temperature, and 98.3 came from our sample, and you'll notice that our sample mean is below the conventional 98.6 value. So we take this data and we want to make a claim about the population mean body temperature. We're going to claim that the mean body temperature, the population mean, the mean body temperature for all people is less than the commonly accepted value of 98.6. And putting that in mathematical terms, we're claiming that mu, the population mean, is less than 98.6. So that sentence, the population mean body temperature is less than 98.6, is written very concisely with this simple mathematical inequality. In this case, mu is the population mean body temperature of all healthy adults. So here's the game plan. We're going to make an original assumption that the population has a given property. In our first case, we claim that P is greater than 0.5, so our original assumption will be, all right, maybe P equals 0.5. Right, maybe the population proportion equals 0.5. In the second case, we say maybe the mean body temperature for all people is 98.6. Right, we're claiming that it's less than that, but let's start off assuming that it is that. And then we find the probability observing our sample statistic. In this case, we'd say, what's the probability of getting a p hat equal to 0.5? Right, the probability of getting a p hat equal to 0.55, and then, or in the other example, what's the probability of getting an x bar of 98.3 under the condition that the actual mean is 98.6, right? And if that probability is really super small, then we can say, well, I bet this original assumption was wrong, and some other assumption is true. And so that's the game. We sort of set this assumption up to possibly be rejected, and then what you're left with is the alternate assumption. So I have some players here. The claim is the statement you want to support. So those are those original mathematical inequalities that I put boxes around from the first two examples. The claim is that P, the proportion of all commuters who use cell phones, is greater than 0.5. The claim is that mu, the population mean body temperature, is less than 98.6. So that's my claim in mathematical terms. In the null hypothesis, denoted H naught, the naught is, or H sub 0, also called H naught, and in this case called the null hypothesis, it's the original assumption about the population parameter. We're going to say, all right, so here I'm claiming that P is greater than 0.5. Let's set up for an assumption that P equals 0.5. And for example 2, we'll say, all right, let's set up the assumption that mu, instead of being less than 98.6, is actually equal to 98.6. Right? Okay, and notice there's always an equal sign in the null hypothesis. Often, but not always, we want to reject this. In both of our examples, we want to reject this original hypothesis, right? We claim that P is greater than 0.5, so we'd like to reject that. And in this example here, we're claiming that mu is less than 98.6, so we would like to reject that null hypothesis. Okay. So then, can't seem to erase that. There we go. So then we have the claim, the null hypothesis, and now we have the alternate hypothesis, denoted H sub 1. And it is different from the null hypothesis. Often, but not always, and we'll get into this in a little while, you want this hypothesis to support your claim. So in our case, for example 1 and example 2, we actually do want this hypothesis to support the claim. So that's the alternate. So if we end up rejecting that, the null, we're stuck with the alternate, which is what we wanted to support in the first place. That's our claim. In the second example, the same thing. If I end up rejecting this hypothesis, I'll end up accepting this one, which was the claim. Right? So I guess it's worth noting, just for the sake of clarity, that in this case the alternate and the claim are the same. And that's often the case, but not always. There are exceptions. All right, moving along. We have 3 players, the claim, the null hypothesis, and the alternate hypothesis. Now, choosing these is critical. There's a lot of math that we'll be doing in a second, but choosing these hypotheses and setting them up correctly is so critical, because if you don't get it right, you wind up just sort of lost wandering through the woods, right? So you really need to set these things up. So here's the process. There's a few different ways to do this, but this way works. Identify the claim you want to support, right? For example, we had the mu is less than 98.6, right? And the null hypothesis must have an equal to sign, so that would be mu equals 98.6, right? And then the alternate hypothesis, it has to be different from the null, right? Because if you're going to reject the null, you got to have an alternate that is different, right? You can't reject one thing and then accept the same thing. And if possible, have it match your claim. And every once in a while, that won't be possible. Okay, so for example 1, our claim was that P is greater than 0.5, representing most commuters use cell phones. So the null hypothesis gets the equal to, the alternate gets the claim because it's different from the null. And the second one, the mean body temperature is less than 98.6, is the claim. The null gets the equal to sign, and the alternate is the same as the claim. Because it's different than the null, I'm good to go. The claim in this such a case, suppose I was doing like, I claim that the mean amount of Coke in all 12-ounce cans of Coke is 12. Suppose I had a claim like this, right? Then my null has to have the equal to sign. And now I've run into this problem where it has to be different. So the alternate it has to be different from this. It can't be the same as the null. I'd like it to support the claim, but it can't. It can't be the same as the claim because it has to be different. So whenever you have a claim of equality like that, you wind up with an alternate hypothesis that has a not equal to. So the alternate is that mu does not equal 12. And that's what's known as a two-tailed test, and I'll describe why that is in a minute. Likewise, you might have claimed, all right, I claim the mean is not equal to 12. Well, the null hypothesis always gets the equal to sign, and in this case I have to have the not equal to sign because it has to be different from the null. The alternate has to be different from the null, and support the claim if it can. So I'm good. I get to be different from the null and support the claim. Right? So it's not that complicated. If you follow this procedure, you'll always get the right claim, null, and alternate hypothesis, provided you know what to do in this circumstance. Right? If you have a claim of equality, you're going to wind up with a not equal to here. And if you have a claim of not equal to, you're going to wind up with a not equal to. Right? If you have less thans or greater thans, you're good to go. Okay, so here's some examples. These are your turns, so they're not in your book. Express each claim symbolically, then find H0 and H1. So the mean heart rate of all men is greater than 75 beats per minute. So the claim is that mu, the mean heart rate of all men, is greater than 75. Right? The null gets the equal to sign. The alternate supports the claim, because it can do so and still be different from the null. Less than 10% of Americans use public transportation. That's a claim about a proportion. The proportion of all Americans who use public transportation is less than 10%, 0.1. And you have to make sure that these proportions are in decimal form. The null gets the equal to sign, and the alternate supports the claim because it can. The mean volume of fluid in all 12-ounce Coke cans is 12 ounces. So what I'm saying here is the mean volume in all 12-ounce Coke cans is 12. The is replaced by an is equal to 12. So there's my claim. My null gets the equal to sign. The alternate, it would like to take the claim, but it can't because that's the same as the null, so I'm stuck with the not equal to sign, right? I would like to make it mu equals 12, so it's the same as the claim, but I can't because that's then my null and alternate would be the same, and that's not a good way to run a test, right? You don't want to reject one hypothesis and accept the exact same thing. So we've got a not equal to sign, and notice that came from a claim of equality. That's when we get the not equal to and a two-tailed test, which we'll talk about in a minute. Most people love pizza. Here, most is just a statement about a proportion. That's a statement that the proportion is greater than 0.5. So this is the proportion of all people who love pizza is greater than 0.5. So it's more than half or most. So that's our claim. The null gets the equal to sign, as it always does, and the alternate supports the claim. So that's important. Setting all this up, it seems fairly trivial, but it's important because if you get going down the wrong path, you can really wind up lost later on in the process. All right, so here's some more players. We have the test statistic, and there's, depending on what kind of test we're running, the test statistic is different. For example, for our proportions problem about cell phone users, this is our test statistic. And for our test about the mean body temperature, this is our test statistic. And these will be given later in the chapter. But basically, it gives sort of how extreme the observed value is. For example, that 0.55, that 55% of cell phone users, came up with a z-score of 1.22, which is not all that extreme. But the 98.3, that body temperature, that has a t-score of negative 3.33. And the t distribution is similar to z, so this is pretty extreme. All right, the negative 3.33. The rejection region is the set of all values of the test statistic, these things, right, that cause us to reject the null hypothesis. That makes us say, oh, that's so extreme, I'm going to reject my original assumption. The significance level, denoted by alpha, is the probability that the test statistic will fall in this rejection region, right here, when the null hypothesis is actually true. This is a type of conditional probability. It is the probability that we end up rejecting the null hypothesis when in fact it is true. Right? So it's an error. It's the probability of an error, right? And the common choices are 0.01, 0.05, and 0.10. And then the critical value is any value on the boundary of the rejection region, right? Those delineate places where we reject the null hypothesis from where we don't. And that's with regards to our test statistic, when this test statistic is too extreme or not. How extreme is too extreme is determined by our critical values. So let's find some critical values. I'll show you how to do this in a second. Using a significance level of 0.05, find the critical z-values for each of the following alternative hypotheses. Sketch the normal curve and the rejection regions. So here's the idea. So if I look at this, H1 says that the mean is less than 98.6. So what that means is a left-tail test, which means my rejection region is to the left, right? And so what I need to do is put 0.05 in the left tail and find out what that value is. And if I put 0.05 in the left tail of my z distribution, and I'm going to have to open up my, I'm going to have to find that. Okay, so now we'll go back. So I'm looking to put 0.05 in the left tail. So I know I'm going to be in the negative zone. All right, negative z. I'm looking for 0.05 inside the z table. And when you look around, that's inside here. What you'll notice, we've done this before, it's straddled between these two. All right, between 0.505 and 0.0495. But you'll notice there's a dot there. That dot corresponds to this dot, which means the z-score is negative 1.645. So that's where this negative 1.645 came from. So if my test statistic winds up in here, that's too extreme, and I will reject the null hypothesis, my original assumption. If it's a right-tailed test, that means I have an alternate hypothesis with this greater than sign. Then I need to put 0.05 in a right tail. So that means this 0.95 is to the left. So I actually have to look for 0.95. By the way, you could probably guess if this is negative 1.645, this is going to be positive because of the symmetricness of the because the z distribution is symmetric. Okay, so I need to get 0.95, so now I'm in a positive number. And if you look around, again, you'll notice you're here, there's a dot. So the 0.95, the z-score is 1.645. So that's where that z-score came from. Critical value, 1.645. So if I get a test statistic that winds up way up here, I'll reject the null hypothesis. If I have a two-tailed test, that means my null hypothesis has this not equal to sign. Then I'll reject the null hypothesis. Sorry, this was the alternate. The alternate hypothesis has the not equal to sign. The null hypothesis will always have equal. Alternate has this 1 here. Okay, so the alternate has a not equal to sign. That means I'm going to reject my null hypothesis if my test statistic is either too high or too low, right? Too far away from 98.6. So I actually have 2 rejection regions. But since I'm at a significance level of 0.05, the total rejection region has to have area 0.05. So this gets half of it, the left tail, and the right tail gets the other half. So I have to get 0.025 inside that left tail. So I look for 0.025 inside my z table. I know it's a negative value. 0.025. When I look around, I find it right there. All right, I'm looking for 0.025 now. 0.025, I found it right there. But that's not what I was looking for. I was actually looking for the z-score. So that's negative 1.96. So my z-score is negative 1.96. That's this one, negative 1.96. So by symmetry, this one's going to be positive 1.96. So I actually have two critical values and two rejection regions. All right. And it's something worth noting. I want to show you at the bottom of the z table here. There's a handy cheater table underneath both of them. It's right here. On that last example, we were at the 0.05 significance level, right? Here are my critical values. For a left tail test, we found it was negative 1.645. For a right tail test, positive 1.645. For a two-tailed test, plus or minus 1.96. So you have this sort of cheater table, so you don't have to go through that whole process of looking for values inside the table. And we have our three popular significance levels, 0.01, 0.05, and 0.1. So that's going to help us out. It's going to save a lot of time. Okay, your turn. Use a significance level of 0.01. Find the critical values of z for each of the following alternative hypotheses. So if the significance level changes, the critical values change and the rejection regions change. If I have a left tail test, as indicated by the less than sign in my alternate hypothesis, I need to put 0.01, that's the significance level, in the left tail. So if I'm looking for 0.01 in the left tail, whoa, went too far. I'm looking around for 0.01 inside here now. 0.01. And let's see, I have 0.0102, 0.0099. Which one of these is closer? The 0.099. It's pretty. They're both pretty close, but the 0.0099 is closer to 0.01. Right. So the critical value is negative 2.33. By the way, okay, here, I went and looked that up again, but look, significance level 0.01, left tail test negative 2.33, right? So the cheat sheet's very handy. So this critical value, negative 2.33, so that's what this value is, negative 2.33. So if I get a test statistic that falls to the left of negative 2.33, it resides in the rejection region. Playing the same game with a right-tailed test, and I'll just go straight to the cheater sheet because that is so fast. It's a right-tailed test. So it's positive 2.33. So this value is 2.33. Anything to the right of 2.33 falls in the rejection region. And if I have a two-tailed test, I have to take my significance level, 0.01, split it in half, and put that amount into each tail. So you can look up 0.005 inside the table. And if you did that, you're looking for 0.005. You'd find that it falls here, and there's the star. So you get negative 2.575. But again, that is in the cheater table. 0.01 significance level, two-tailed, plus or minus 2.575. Love the cheater table. So plus or minus 2.575. So this one's negative 2.575, and this one's positive 2.575. And I have two rejection regions. So if my test statistic is either too big or too low, I will reject the null hypothesis. All right, now we talk about the p-value. The p-value of a test statistic is the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data. It is basically a measure of this test statistic's extremeness. It tells us how extreme is this test statistic. So we're going to do some examples. Determine the null and alternate hypotheses for the given claim. Determine whether the test is left, right, or two-tailed, and find the p-value. That's sort of the new stuff right there of the given test statistic. So I claim that some population proportion is greater than 0.25. And I get a sample data that produces a test statistic of z equals 1.18. So again, from this claim, my null gets the equal to sign, and my alternate supports the claim. Because of this greater than sign, it's a right-tailed test. So if this is my 1.18 right there, that's my test statistic, then the p-value is this area, this shaded region. It represents the probability of getting a test statistic more extreme in the right-tailed sense than the one you got. So we have to look up 1.18 in the z table. And when we get 1.18, it's a positive value. 1.18, 0.8810. But I'm looking for area in a right tail, so that 0.8810 is actually that area. So the p-value is 1 minus that. So this 0.119, that's the p-value. That tells us how extreme this test statistic is. It's not that extreme. You'd expect about 12% of the z-values to be even greater. Number 2, I claim that p does not equal, some population proportion does not equal 0.25. And the sample data produces a test statistic of 2.34. To get my null always gets the equal to sign. In this case, the alternate can support the claim and still be different than the null, so I'm good to go. And because of this not equal to sign, this is a two-tailed test. Right? And so if I look at 2.34, that's this value right here. So anything bigger than 2.34 is more extreme than 2.34. But in a two-tailed sense, anything to the left of negative 2.34 is also more extreme, right? Because if you're looking at both sides of the zero, more extreme than 2.34 can be in either direction. So basically this total shaded region is the p-value, right? And so if we look up negative 2.34 in our table, negative 2.34, get rid of that for now, and all that. Negative 2.34, 0.0096. But that's in just the one tail, right here. So this one by symmetry has the same area, so I double that and I get 0.0192. So this describes the extremeness of this test statistic in a two-tailed sense. Your turn. You claim that some population proportion is less than 0.25, and the sample data produces a test statistic of negative 1.85. To get the null hypothesis, I impose an equal sign, and the alternate gets to support the claim. Because of this less than sign, this is a left-tailed test. And so if this is my test statistic, in a left-tailed sense, anything to the left of negative 1.85 is more extreme than negative 1.85. So I just need to find the area under the curve to the left of negative 1.85. And that's the easiest thing to do. We just go to the table, negative 1.85. Let's see. negative 1.85. Looks like I'm 0.0322. So that's the p-value. So its extremeness with respect in terms of a left-tailed test is 0.0322. That's pretty small, meaning that only about 3% of these z-values are more extreme than negative 1.85 in a left-tailed sense. So for decision making, we have to decide whether or not we're going to reject the null hypothesis. All right? And we're going to base it on the extremeness of our test statistic. There are two equivalent ways. There's the critical value method, where you reject H0 if the test statistic falls in the rejection region. That's actually why it's called the rejection region. And then you fail to reject H0 if it doesn't. And then the p-value method, you reject H0 if the p-value is smaller than the significance level. Right, so if the p-value is small, particularly smaller than the significance level, you reject the null hypothesis. And you fail to reject the null hypothesis if it's not. And these are actually identical. You'll never reject under one system and fail to reject under the other. And basically, for example, if I look at a left-tailed test at the 0.05, so suppose that's the significance level. And this is the z sub alpha. Basically, this is the rejection region, right? And so if I'm to the left of z sub alpha, the test statistic is in the rejection region. Likewise, if it has a smaller p-value, if the p-value is smaller than alpha, that means it's over here somewhere, my test statistic, which means it's in the rejection region. So these are identical. And it tells us whether to reject or fail to reject the null hypothesis. Notice we don't accept the null hypothesis. We just fail to reject it. Right? An important piece of terminology. So here's a complete example. We will test the following claim at the 0.05 significance level. This is that first example. Survey showed that of 150 randomly selected commuters, 55% have used a cell phone while they drive. We want to claim that most commuters use cell phones when they drive. So the claim, we've already gone through this process a little bit. The claim is that P, the proportion of all commuters who use cell phones when they drive, is greater than 0.5, more than half. The null gets the equal to sign. The alternate supports the claim because it can. The info, the sample proportion, it's 0.55. By the way, if you're wondering why I'm looking for all this info, it's because I'm looking down here at this test statistic. So I'm going to need everything in there. The value P in this formula is the proportion from the null hypothesis. So that gets a 0.5. And Q is always equal to 1 minus P, so 1 minus 0.5 is 0.5. I also have an N in there, that's 150, my sample size. And my significance level is 0.05. So that's just some preliminary info. Is this a left, right, or two-tailed test? This is a right-tailed test. Right-tailed test because of that greater than sign. You look in the alternate hypothesis, and the alternate hypothesis tells you whether or not it's left, right, or two-tailed. And then the test statistic, and we'll get into this in the next chapter, is given by this formula. So we put in P hat, P from the null, P again, Q over N. Plugging all that into my calculator accurately, I get 1.22. So that's my test statistic, all right? Big player. It describes, that's what we're going to test, right? How extreme is that? So let's do critical, we're going to check the critical values of Z. So this is a right tail test at the 0.05 significance level. This critical value was found from that little table, and I'll use a little cheater table because it's one of the popular ones. So the significance level was 0.05. It was a right-tailed test. A critical value is 1.645. So that's where I got my critical value. And because this is a right-tailed test, the rejection region to the right. Is the test statistic in the rejection region? No. 1.22 is over here somewhere, right? It's to the left of 1.645. No. So the conclusion about the null hypothesis based on this method, we fail to reject. The test statistic is not in the rejection region, so we fail to reject the null hypothesis. Now let's take a look at the p-value of our test statistic. So there's our p-value, or there's our test statistic, sorry. That's the test statistic. And the p-value is a measure of the extremeness of this 1.22, which is the probability of getting something greater than 1.22, because this is a right-tailed test. So if I look up 1.22 in my z-table, now I'm not looking for it inside the table. I'm looking for it as a z-score, 1.22. Let's see, 1.2, 2.8888. Gotta be careful, I don't want to say too many 8s. But that's the area to the left. So the area to the right is 1 minus that. And the p-value is 0.1112. Is this less than alpha? No. Alpha is 0.05. So this is actually bigger than alpha. So the conclusion about the null hypothesis based on the p-value method, because the p-value is greater than alpha, again, you fail to reject the null hypothesis. What's important is these two will never disagree. And you really only have to do one way. As we get further into the chapter, sometimes you'll do one method, sometimes you'll do another method. But to complete the hypothesis test, there's no need to do two, unless you're specifically requested. So by the way, the concluding statement that comes out of this is, the 55% from my sample was indeed more than half, but it wasn't far enough over 1/2 to support the claim about the entire population. So what we say is there is not enough data to support the claim that most commuters use cell phones when they drive. We're not saying that most of them don't. All we're saying is that the sample most of them did, but it wasn't far enough it wasn't large enough for us to make that claim about the entire population. All right, so the phrasing of these conclusions, because these conclusions are pretty important. You don't want to say the wrong thing, because we didn't prove that most people didn't use cell phones. We just said there's not enough to prove that most people do. All right, so here's the idea. So this is the phrasing of conclusions. This is an important page because all hypothesis tests have to end with a concluding statement. If the alternate hypothesis supports the claim, which is what that example was, then we're going to use this box. So from this previous example about the cell phones, if you look at this, the alternate hypothesis and the claim are the same. So we're in that first box. Back down to here. Had we rejected the null hypothesis, which we didn't, that would have been good. And we would have said the data supports the claim that most commuters use cell phones when they drive. As it was, we failed to reject the null hypothesis. So we said there is not enough data to support the claim that most commuters use cell phones. Right? If the null hypothesis had supported the claim, and that's a little harder because you'd have to have a claim of something like mu equals 12, and then the null hypothesis would be that mu equals 12. So you'd wind up with a two-tailed test. All right. So if that's the case, but if you have something like this, then you're in this box, right? If we reject the null hypothesis, that's not good, because if you reject the null, you've actually rejected the claim. So if you reject the null, you say there's enough data to justify rejection of the claim, and then whatever your claim was, in sentence form. And if you fail to reject the null hypothesis, that's actually good, but you don't really get to accept it, but you failed to reject your claim, right? So there's not enough data to justify rejection of the claim, right? So this is a good box, at least especially when you do your first few tests, to come back and check these situations out to get your proper phrasing. So here's the idea. If we fail to reject the null hypothesis, we did not prove it was true. We just didn't have enough evidence to reject it. We never accept the null hypothesis. And it goes like that in a courtroom analogy. The null hypothesis is that the defendant is innocent. You go in there, presumed innocent. And the alternate is that the defendant is guilty. And when the jury comes back, they can say, all right, you've provided enough evidence, we reject this, and we come back with a guilty verdict. All right? But if you don't provide enough evidence to convict, then they say, all right, we can't reject this. And so the courtroom, the jurors come back, they don't say we find the defendant innocent. They say we find the defendant not guilty, right? He didn't provide enough evidence for us to believe that he's not innocent. Okay, so we never really prove innocence, just like we never really accept the null hypothesis. There are two types of errors. A type 1 error, this is an error of rejecting the null hypothesis when it's true, right? That's one type of error we can make. And the probability of this type of error is alpha. That is actually the significance level. So we actually have a good way of quantifying the probability of a type 1 error. It is a type of conditional probability. It's the probability of rejecting the null hypothesis under the condition that it's true. A type 2 error is not rejecting the null hypothesis when it's false, right? And that's always a possibility as well. The probability of this is denoted beta. Calculating beta is difficult to do. The power of the hypothesis test is 1 minus beta. We're not going to talk too much about beta. But there is a relationship between these two probabilities. So we have a probability of making one error and a probability of making another error. So for any fixed sample size, if you decrease alpha, right, that decreases the probability of a type 1 error. That simultaneously increases the probability of a type 2 error. Right? So if you make it, so if you decrease alpha, that maybe makes your rejection region really small. Then you have a much higher chance of having a test statistic, say, wind up over here, and you're not rejecting the null hypothesis when you maybe should. So you can't, and if you increase alpha, beta goes down. So the relationship looks like this between alpha and beta. If you increase alpha, you have the less likelihood of a type 2 error, right? So if you increase the probability of a type 1, it decreases the probability of a type 2. If you decrease the probability of a type 1, it increases the probability of a type 2. Well, there's really no way around that. The only thing to do is increase the sample size. If you increase the sample size, it will decrease both probabilities of the two different types of errors. And again, at stevenstats.com, they have how you do a lot of these tests with software. And it gets through a lot of the grunt work. But even with software, you have to be careful because the setup is so critical. And if you don't set it up correctly, you get back these p-values that are bigger than 0.5. You can really mess things up if you don't understand the mechanics of what's going on in the background. So software is not really your way out of the problem of figuring out how to do these tests. Okay, so that wraps up what I believe to be probably the longest section in these videos. And so we're going to start doing some actual hypothesis tests in 8.10. I hope to see you there. Have a good day. Bye.